All right, everybody. So today we're going to continue on learning on how to interface with the Arduino and do some more programming today. Something that's actually a little bit more involved than the real simple examples we did last time. But first, we're going to talk about using digital input output, or I/O. So that's what we're going to do first in the lecture. So, like I said, I/O, which is what you will pretty much always hear, stands for input and output. And by digital means, that it is a either a square or a discontinuous or stepping, right? It comes in discrete values, as opposed to like an analog signal, which is something that would be a smooth, continuous wave, right? So pretty much any sort of microcontroller or computer operation is going to use digital interfaces and digital I/O, right? Because all of your computational math is based on integer digital math, right? So you can use digital I/O for all kinds of controls and interfaces. Anything that's just a simple on-off indicator, like a LED, a lamp, an audible alarm, right? Those are all very easy to control digitally. You can actually easily read the state of anything that is a simple on and off itself. Like, hey, is this switch in an on position, right? That's the simplest sort of thing to do because it's only got one state. Now there's much more complicated things that you can actually do with digital I/O. You can control motors, i.e. control the speed, right? Because you could easily see that, hey, I could turn a motor on or off, but what about controlling a variable speed, right? But that is something else you can do with digital I/O, and obviously that's a little more complicated. Similarly, you could control the position of solenoids or electrically controlled valves. Obviously, any sort of user interface like your keyboard is done over digital. We're gonna later learn in the semester how to communicate with other integrated circuits using some serial protocols, but that's still digital input. And, like configuring multiple options, all of this stuff is digital input and output. And, it's somewhat odd to list some examples where basically any sort of communication that you're going to do with the Arduino is digital input and output. So just to sort of give you a graphical example, right? This is an example of, or a cartoon example of a digital signal and an analog signal, right? So we will cover some time varying analog signal stuff later in the semester, but this is just sort of an example, right? We don't really need to know what this is. This isn't a real signal. This is just sort of an arbitrary example. But the point is I can see this thing is continuously varying and it's a nice smooth curve. Whereas a digital signal is, right, I have these step changes. I'm either at this value, discrete value, or this discrete value. You could also create something similar to this where you broke this up into multiple steps. I'm not necessarily limited to a single on-off value. Obviously, that's how stuff like digital audio works, is I'm breaking that up in, yep, I would break this up into multiple steps, but we'll talk about that all later. So sort of the point is that most real physical signals in the real world are analog, right? There's, a continually varying pressure that you're feeling. That's what's making sound. It's not in steps of, every PSI, or, if you look at light with your eyes, you can see that it varies sort of continuously in color and intensity. So the question then becomes, how do we create these digital signals, which is what we have to use for our processing, our electrical processing, out of, these analog physical signals? So, like we said, digital signals are, where you're having discrete changes in voltages. They're not smooth. Often you just have two values, a low and a high, if I'm talking about logic, right? Where my 0 and 1, or a true and false. So one thing that's important when you talk about any sort of digital interface is you have to define what the levels are for that high and that low is. So those are called logic levels. And basically they're the thresholds of what's a 0 and what's a 1, i.e. what are the levels, the voltage levels that correspond to the logical values, right? And if you look up any type of electronic logic, this example here in particular is for the Arduino, which is also based on what's called 5-volt TTL, which is transistor logic. I forget what the second T stands for is. But there are many other varieties of logic level. There's very common a 3.3 volt logic level. There are other 5-volt logic. There's like CMOS logic levels, and they're going to be slightly different. So you want to be able to look up a chart like this so you can tell if you're using multiple logic levels, are they compatible with each other? So what you see here is the highest level is going to be what's like your CC voltage. That's the voltage that you're supplying basically to your power, right? And then obviously the lowest is going to be 0 or your ground. But then you're going to see these other 4 symbols, VOH, VIH, VIL, VOL. And what these are is they are either the minimum or maximum values for that to be considered a high or low, and then on the input and output, right? So VOH is the voltage output high. So for this particular logic standard, if I'm outputting a high from this circuit, that signal will be at least 4.2 volts. It may be all the way up to 5, but they're sort of guaranteeing the lowest value that this electronics will output when it's outputting a high value will be 4.2 volts. VIH is the minimum value to be considered a high voltage or a high. So anything on the input greater than 3 volts will be interpreted as a high by this logic. And you can see this makes sense that the output value that it's for outputting for a high is larger than the minimum value that it will accept as a high. So I'm sure you could probably figure out these other two, but VIL is voltage input low. So anything below 1.5 volts is going to be considered a low on the input. And then when this electronics, the Arduino in this case, is outputting a low value, it will be at most 0.9 volts, right? So you can see if I had two slightly different logic levels, I should be able to look at the two sets of these values and figure out, hey, is the output of the high output from this other one going to be correctly interpreted as a input high on this second piece of electronics, right? Normally, you try and work all within a common logic level system, if possible, so you don't have to worry about that. But if for some reason you have to, this would be how you would figure out if they're compatible. Yes, I have a question in the room.
Yeah. What is the space between 1.5?
So I was just asked basically, what is the space in between the 3 and 1.5 volts? And that is basically what you would call indeterminate. So nothing that is involved in the digital logic of this should ever output a signal in that range. And conversely, you don't really know what is going to happen if you have that as an input signal. So you should not see any voltages within that range. Obviously, in the real world, things break and malfunction, but you will basically get odd behavior in this range. So this is, again, what I just went over, right? VOH, minimum output high. VIH, minimum input high, right? Similarly, output low, input low, right? So, like I said, it sort of makes sense that all of the outputs are to the extreme, closer to the 0 or the 5 compared to the inputs, right? Because you want the thing, the circuit should be designed so that it will read its own highs as highs, right? So, and its own lows as lows. And again, here is the answer to the question we just talked about. So there is that gap between the voltage input high and the voltage input low, which is the 3 volt to 1.5 volt gap, right? So you shouldn't ever see anything in there. And also that has the advantage of, that's what gives you a nice clean signal, is you have good separation between your low values and your high values, which means you should never get an input or a low input interpreted as a high and vice versa, right? Because, I have to somehow, screw up the signal by almost 1.5 volts before it misinterprets the signal. So like I said, you refer to this as the logic level, and for each component, right, will have its own particular logic level, and these are grouped into common logic level families, like the 5 volt TTL, 3.3 volt CMOS, right? These are basically a group of components that should have a consistent logic level. So now we're going to talk about a few different types of these digital I/O signals, right? So I think we may have covered this back in the early basic electronics, but there's basically, two versions of current flow. There's DC, direct current, and AC, right? And the difference is whether or not you have basically only flow in one direction, right? Which also corresponds to the current being only positive. Or you could have current that will reverse direction, right? Like your AC distribution, which means the current goes from positive to negative. So another way to refer this is DC components are unipolar, i.e. one sign, right? One direction, uni. And AC are bipolar because it can go both ways. And then there's a third way of doing digital signals that we'll also talk about here called pulse width modulation, which you may recall that I talked about. There's a certain group of pins on the Arduino that are capable of outputting PWM signals. So, simplest thing here is a unipolar digital I/O signal, right? There's one value of 0 for your low, and your value for high is 5 volts in this example, 3.3 volts. 1.7 volt is another standard that you'll see. But the point is I have two levels. One of them is for the low, the logical 0, and the other one is for the 1, right? So that sort of also brings up the question is, how do you know if you're sending a 0 or if you're just not sending anything, right? So you don't really have a way of telling, but usually this is accompanied with some sort of clock signal so that you're indicating when you want to look at the actual value, but that's just a quick example. So in bipolar, you have two cases. One where you basically, so usually that means you have a positive value for the ones or the trues and a negative voltage value for the zeros. In fact, the RS-232 protocol, that is the old style serial port that you may run into, not USB, but the big one that looked like a monitor plug, uses something like this. It uses a plus and minus 12 volt signal. But here again, there is two versions of this. One where you basically are very similar to the unipolar, where you only are ever in the 0 or the 1 state. Not 0 volts, the 0, so the false -5 volts, or the positive 1 true state, right? That's what this example is here. And that's called non-return to 0, right? Because the signal does not return to 0 when it's idle. Alternatively, you can be in this state like this, where you have a return to 0 state, right? So you basically have 3 possible states. You have your false, your 0, and your true. But then you have this idle state which is indicated by the fact that when the line or the signal is at 0, that means this is not a signal. I'm just sitting idle. I'm not trying to transmit anything. All right. So now, what about this pulse width modulation, right? And I may have mentioned this previously, is it gives you this sort of quasi-analog signal. And this is how you're going to do stuff like control motors or control the position of a servo. So it's not really an analog signal because it is a digital signal, but it gives you a way to have a continuously varying value. So some examples is you can control the speed of a motor. You can control the brightness. In particular, you can control an LED brightness, which is actually a bit tricky to do because an LED is not like an incandescent light bulb where you can just send more current through it to get brighter. An LED is pretty much either on or off. You can control the direction of a servo. A servo is just basically a motor that instead of spinning continuously, it moves to a specific angle position, right? And you could also use this for more advanced communications. So you may be able to guess how you do this by the name pulse width modulation. So what we have is we have a signal that repeats itself on some predefined period, right? So each one of these you can see is a separate period, right? Here I have, in this case, I'm using the symbol T for a period. So here's 0, here's half a period, here's a full period. And then I start over, half a period and a full period. So this entire thing is a single period. You'll notice that during this entire signal, it is still always only 0 or 5 volts. It's only off or on. But what I can instead do is I can vary how long that I keep this signal on. In this case, I have it at 50%, right? But there's no, I don't necessarily need to keep it that amount, right? So if I have this thing that, you know, the period is T and I want to get a signal of about 2.5 volts, well, if I leave that on for 50% of the time, that averages out to 2.5 volts, right? And the point is I'm going to repeat this. This only works if I know that this pulse is some fixed width, right? Because if this total period length changes, I can no longer tell, well, was it on, you know, if that length can vary, when I look at the positive pulse part, I don't really know what percentage it was. So what you get is you get a signal that looks like this. It's, you know, that's called a square wave. And you call the percent time that it's on, that's the duty cycle. That's when it's doing work, if you will. So like I said, if I can then basically average the voltage value over the entire signal to get an average voltage, right? So if I have 2.5, if I want a output of 2.5 volts on average, well, and my positive value is 2.5, I just turn it on for 50% of the time. So what that means is I can basically change what that average output value is by varying the fraction of the time that I have it on, right? And that basically gives me a variable output all the way from 0 to 5 volts, right? Because I can basically turn it on in varying amounts from 0 to 5 volts. And it turns out that you can actually pretty easily put some kind of averaging circuit consisting of a, you know, a couple of capacitors and resistors on the output, and it'll actually basically smooth out that average. Or if I'm dealing with something like an LED, if I'm doing this fast enough, your eye can't really tell that I'm actually flicking the light of the LED on and off real quick. It will do the averaging itself. It will be like, okay, when I have it on 100%, it looks this bright. When I have it on 25%, it looks, you know, a quarter as bright. So this is how you get that analog-like signal out of something that's purely digital. So one of the things we talked about was, how do I tell that I'm actually sending a 0 or I'm just not sending anything, right? And then you also may want to think about, well, what happens if I read one of the pins? What is the logical value of a pin that doesn't have anything connected to it, right? Well, it may be a 0 or it may be a 1. This is actually referred to as the pins being floating. And the other thing is it high? Is it going to be perfectly 5 volts, right? And the answer is no. And basically, we don't want stuff to be sort of randomly not having a clear signal of its 1 or 0 while we're using it. So what we actually do is we will connect resistors to it. We will either connect the pin through a resistor to a positive 5 volt signal or to ground. And these are called pull-up resistors when they connect the input pin to a positive, a high, the upper voltage, or a pull down when it's pulled down to 0. And what that means is when I don't have an input signal here on the IO pin, or well, actually, this would be the pin on this side, and then the signal that you actually care about is here. What that means is I know the pin is in a known state when I don't have an actual signal here. So also, that's not going to mess up the signal when I have it's not going to interfere with the signal when I actually have a signal of 0 or a signal of 5 here. So for example, when I have a signal of 0 here, well, I'll just have enough current. I mean, the drop across here is going to be 5 volts, right? Because there's no resistance between the pin and the signal of 0. So the pin will see the 0, and what I'll have is a difference of 5 volts across there. Same thing here. And conversely, when this is at 5 volts, well, that just means it's at the same voltage here. There's no current across here. And then there is a 5 volt signal. So basically, anytime you are using a digital signal, you will want to use a pull-up resistor or a pull-down resistor. And in fact, most or a lot of microcontrollers have these pull-up and pull-down resistors built in to the circuit. So this gets rid of that unpredictable high and low state when you don't know what's going on, right? So there's going to be possibly stray little inductive charge paths or discharge paths on the board. So if I didn't have a connection to ground or connection to a positive voltage, those pins would be in some unpredictable state. And in fact, you could probably, it's really easy to see this if you try and read the state of a pin that doesn't have anything connected to it. You sort of just get random values. So because of this, like I said, you pretty much always want to use a pull-up or pull-down resistor. Usually the actual value doesn't matter that much, right? Because I'm not actually looking for a particular resistance. I'm just trying to put some resistance between the input pin and either the ground or the voltage source so that I have that voltage drop. It can start to matter when you start dealing with rapidly changing signals, like like you would for serial pins, i.e. if I'm trying to communicate very rapidly across that pin, right? So if you recall from what you learned about with the Skeeter sat, is when you have a resistance and some capacitance, you have a time constant. So you'll have a charging and discharging time. So, and that the value of that time constant depends on the product of the resistance and the capacitance. So if that time constant gets to be large compared to the, the length of my signal pulses, well, now I'm not actually, my nice square waves will start to get rounded off, and I may not be all the way up to the positive value by the time the pulse is over. So I could start interfering with signals, but that really only becomes a concern when you're talking about like very rapid signals, when you're trying to do like megahertz speed communications. Or it could potentially be the case that you just have a lot of different things connected to that pin. So that also could be cause you to have that time constant. So just to go over it again, here's our pin layout. Here are your digital pins here. These are your analog pins over here, but these are also usable as digital pins, but they are the only ones that have analog capability. You've got this block right here that is mainly for power, right? So it's like either a 3.3 or a 5-volt signal or ground, or you can feed power in here. Most notably, over here are your pulse width modulation pins. So that is a specific hardware capability built into these pins. So if you're going to do PWM, you want to use those pins. Just to remind you guys all again, here's our serial ports, which actually, after you guys did that first activity, you guys were actually using serial 0, which actually comes out the USB as well. But if you were to connect to those pins, you would also have seen the UART communications that you were doing last time. And then there's 3 other serial ports, so 1, 2, and 3. And then these pins down here are for I2C, which is something we'll cover later. But basically, almost all of these pins can be used for general digital input and output. If I want to use something more specific, like pulse width modulation or some of the serial protocols, I need to use these specific pins. But you can see here that they basically all have this gray pin number, including the ones on the bottom. And the gray here is indicating just a general purpose digital pin, i.e. I can flip each one of those pins on and off. Yes?
So in our program, are we going to use the digital pin or the analog?
So we will be using, today we will be using digital pins. So I was asked if we're going to use those. So yes, so we will eventually use the analog reading pins. So that's what those actually, let me clarify that. These are analog read pins. These are connected to the ADC. So you can read a variable voltage here. So we will use all of those. We will also use several of these serial pins. We will use the I2C pins eventually. But today we're just going to be doing general digital I/O. So again, here's your power block right here. There is also this reset pin, which is not really used directly. I'm trying to, so you have the reset button here. And what that does is it basically, if you connect this reset pin to ground, that just restarts the Arduino. And the reason that they put that on the shield or out on this pins here is you can see the reset button is kind of in the middle here. So if I was to put a shield on top of this, it would block, I wouldn't be able to hit that reset button. And depending on which model of Arduino you've got, the reset pin will also be like up here in the corner. I'll show you on the camera in a second, but yep. So like this says, it resets the board when it's pulled low. But what that means is, all that means is it's the same thing as basically powering the Arduino up and back down, right? Because the Arduino is going to run whatever code is on it. This IO reference pin is going to just be whatever the corresponding high voltage is. So for the Mega 2560, that'll be 5 volt. But there are also 3.3 volt Arduino boards, like the Arduino Do, for example. So in that case, that IO ref would be 3.3 volts. So pins 2 through 13 are your pulse width modulation. 0 and 1 is your serial 0, but in the IDE, it's just single serial. And then you have, oh, I lost it. You have your other 3, so serial 1, serial 2, serial 3 on pins 14 through 19. And you can see each one of these is paired in TX and RX pins, right? That's a transmit pin. So the Arduino will send signal out on the transmit pin, and it will listen for signal on the receive pin. Like I said, these 2 pins here, the SDA and SCL, are your I2C, which is an alternate kind of serial communication. In fact, it stands for serial data and serial clock. We will cover that. In particular, that protocol uses what's called a master and slave protocol, i.e. there's one master device that is sending commands and requesting data from all of the slave devices. Like I said, the SCL is a clock pin, and the SDA is the actual data. We'll cover that more in depth when we start talking about serial communication. You have a couple of, or I guess 3 more pulse width modulate. So this is the one on the, what I would call the bottom header. So this is the thinner one. And then these 4 pins in the corner are MISO and MOSI, S clock, and either CS or SS. So this is used for another type of protocol called SPI, which is a serial peripheral protocol. So in this case, the SCK is your clock pin. The CS or SS is the select pin. So you will actually, if you have multiple devices, you will have multiple select pins. Basically, you pull that pin low to tell the appropriate device, hey, I'm talking to you, as opposed to any of the other things that might be connected on the MISO, MOSI, and S clock pins. And then this is similar to the I2C in that it has a master and slave, but it is also similar to the UART in that there's 2 separate transmission lines. So One is for the master input slave output. So that's where in this case, since your Arduino is almost always going to be the master, it's going to be listening on that pin, and it will be transmitting on the MOSI pin, which is master output slave input. So one thing that you have to be careful of is how much current you either send in to one of these pins or supply out of one of these pins. So in this case, we're looking at supplying current from your IO pin. So that's acting as a current source. So that means, hey, if I have my IO pin as high, I have maybe some kind of load with, let's say, possibly a LED that I'm just trying to blink. And then there's either a resistance from a pull down resistor or just the inherent resistance of the circuit, right? So that means there's going to be this current flow here. But this IO pin is not like a power supply. It's a little bitty IO pin going through some small traces. It's not meant to supply power. It's meant to supply a digital signal. So, you know, if this load is small, that means this, or sorry, if this limiting resistor here is large enough, and, you know, depending on what this load is, this current's going to be small and you'll be okay. And in fact, that's why you want to have this limiting resistor. For example, if this was just a LED straight to ground, there's not really anything limiting the current flow. So I'm going to draw a ton of current there, and I could potentially damage my pin and my LED. So you want to know how much current you should be supplying out of that. And if you look at the specs, there will be basically a maximum current limit that you can supply out of your IO pins. And obviously when this pin is high, the load is on, right? I have current flow from positive to ground. When the pin is low, the load is off, right? And you can have the opposite case where the current flow is going into the pin. You call that acting as a current sink. But again, you still have to worry about that limit, right? Because it's still, that current has to go into this pin and through all of the little small solder connections and traces, right? But the big difference here is when I turn my IO pin low, now I have a path 5 volts through the limiting resistor through the load to ground, right? So I turn this pin low to turn on the load, and I turn the pin high to turn off the load. And in particular, depending on what is on these loads, you probably want to know what the default behavior of your IO pins. Are they going to default low or default high? Because there will be a brief time before your software actually gets up and running when you first power on your microcontroller, right? So you want to set this up in such a way that your load doesn't, turn on before you get a chance to have it really want to be on, right? So some real simple examples of this, like I said, is, hey, I can put an LED, and then I can put a resistor, current limiting resistor. And in this case, if I have the IO pin acting as a source, high will turn the LED on, low will turn it off. But I could easily set it up this way, which would give me the opposite behavior. Turning the IO pin to low turns the LED on, turning the IO pin to high turns the LED off. So, like I said, there is a current limit that you want to be aware of. So the digital pins are limited to 40 milliamps. And what this is saying, they are set to input by default, is that means you can read the pins by default, but you can't write to the pins by default. Now, in the programming, you can actually you use this function, this pin mode function, to tell it, I want the pin to be an input or output. Now, I did just say they default to input, but even if you're using the pin as an input, I would recommend you include the appropriate function call to make sure that it's set to an input, right? You always want to have a positive control where I have defined the state that I want it to be in. So then if you have the pin set to an output, you call the digital write on that pin. So what actually goes in this function in the pin mode is the pin number. And then digital write will have the pin number and then the value. So you can set pin 4 high or pin 4 low to do the appropriate. And then digital read is how you, if you have an input signal going to your IO pin, that lets you read which value it is. So you will call digital read, you will put the pin number in the parentheses, and it will return a 0 or a 1, depending on whether or not you have a high or a low voltage signal. So a 0 or a 5 volt signal at that pin. But what's important is, usually if I'm calling this digital read, I need to stick that into a variable unless I'm going to immediately use it, right? Because if I just say digital read pin 7, I mean, the program will give that value, but the program will then just get rid of it because it doesn't know that you want to keep it. So you want to say like pin status equals digital read 7. And then I can use that pin status variable to do whatever I was trying to do based on the input pin, the value of the input pin. Yes, I have a question in the room.
So how do you, what do you put in those parentheses?
So for the digital read and the pin mode, like I said, so the question was what goes in the parentheses. The pin mode and digital read both only have a single argument, which is the pin number. The digital write has 2 arguments. It's the pin number, so which pin do I want to write, and then do I want to set it to high or low. And here's an example, right? Oh, and in fact, I misspoke, because obviously pin mode can have the value of input or output. So here, this line in the setup, we are calling pin mode. We are setting the mode of pin 13. So that's why pin 13 is the first argument. And this is actually a constant that's predefined. So that's why it's all caps. So it's just all caps output. Now, if you really wanted to know, this output actually will have a numerical value. I don't remember what it is off the top of my head, but this is basically a constant that's defined within the IDE, so you don't have to remember what the number that you're supposed to set for output is, right? And then down in my loop, I'm going to set it to high, right? So I've called the pin again. Again, I've called a constant that is the numerical value for high. I'm pretty sure the numerical values for high and low are just 0 and 1, if I remember right, but it's a lot easier to remember high and low. And then I wait. This delay is just wait for X number of milliseconds, so 1,000 milliseconds in this case. So wait for a second and then set the pin low, right? So this is what this program is going to do, is basically start up, set the pin to output, set it to high, wait a second, set it to low, wait a second. Now I'm at the end of the loop and I go back to the beginning. So now I've set pin 13 to high, wait a second, set pin 13 to low, wait a second, and basically continue to do that until the Arduino is powered off. So for the pulse width modulation pins, there is a function called analog write. And what that is going to do is that's going to set up the how long of that pulse it's going to be on. So also, the thing I don't really like is that it's called analog write, which implies that it's an analog output signal, which it sort of is, but it's not a true analog output signal, right? So if I hooked up a scope to that PWM pin, an oscilloscope, which is something we are going to do next week, is I would see a square wave of varying width. I wouldn't see a varying height voltage signal. So for this particular case, you don't need to use the pin mode function before calling analog write. And then the way that you use analog write is like this. You call the pin number and you give it a value. And in this case, it's a value from 0 to 255. And so that's, as you can guess, that's a single byte, that value. That's why it's 0 to 255. And that's basically the fraction of how long it's on. So 0 will be always off, and 255 will be always on. So if you wanted to figure out, well, what would 50%? Well, it would be 127 or 128, right? You can't actually get the 50% exactly. So, but you can put any possible value in there. So you basically have 255 steps from between full on and full off. So like I said, if we go back to our pin diagram, you're limited to these ones that actually have that hardware PWM functions, pins 2 through 13. And then just as a quick caveat, apparently pins 5 and 6 are going to be slightly higher duty cycle than you would expect. So that's something to be aware of if you were looking to use those two specific pins. But that's it. So that is it for the lecture for today.